So this video is about a spectroscopic technique called nuclear magnetic resonance spectrometry. So it's got something to do with magnets and something to do with nuclei. So back to the electromagnetic spectrum that we keep coming back to. So for this technique, we're using light of very low energy, so in the radio wave region. And it turns out that this low energy is equal to the energy gap between ground and excited state in terms of nuclear spins. So I'll tell you a little bit about what that means. So this is the NMR spectrometer is actually a big magnet, which is shown over here, and the sample of interest is dissolved up in a solvent and put into a glass tube that goes right inside the magnet. And then we have we can send radio frequency energy in through here. So what happens when you put a sample inside a magnet is that, well, before it's in the magnet, the atomic nuclei behave like little magnets and they're oriented in random directions. But when you put a sample inside that applied magnetic field, all the little nuclei which behave like little magnets, they align either parallel or anti-parallel to the applied magnetic field. And there's a very small energy difference between nuclei that are parallel to the applied magnetic field and anti-parallel. So there is the little energy gap that we're going to be exploiting with NMR spectrometry. So what happens now? We've got our population of nuclei. Those little magnets either aligning a parallel or anti-parallel, and there's a slight difference in these populations. So now if we shine some radio frequency radiation, then that will be absorbed by some of these nuclei and they will be promoted up to the higher energy state. And that's the little absorption of energy that we're going to be measuring. So the information we can determine from hydrogen NMR spectra, there's a lot of info you can get out of the spectra. First of all, there's this thing called chemical shift, I'll explain in a moment, which indicates the type of environment that those particular hydrogens are in, the chemical environment that certain hydrogens are in. Then you can integrate the spectrum and that tells you the number of hydrogen atoms, or we'll call them protons, in a particular environment. And finally, something else that we're going to cover in class is a phenomenon called multiplicity that I'm not going to go into now. So I'll show you what a typical NMR spectrum looks like. So this is the NMR spectrum of this molecule here, methyl acetate. And on the x-axis here, we have something called chemical shift that goes from 0 to 10 in the wrong direction. So there are three signals you can see here, three peaks, and I'll explain what those peaks are. The first one's not so important. That's tetramethylsilane, which is just included as an internal reference compound. So these two signals derive from the hydrogen atoms in methyl acetate. So methyl acetate has got two different types of hydrogen atoms. So the first type of hydrogen atoms, these three hydrogens here are all the same as one another, but they're unique within the rest of the molecule. So those three hydrogens give rise to this signal here. And these three hydrogens are the same as one another, but unique within the rest of the molecule. So we'll call these hydrogens another hydrogen environment. They give rise to the other signal. So the reason that so these two hydrogen environments, these two types of protons, they experience a slightly different local magnetic field just because they're in different chemical environments in the molecule. So that's why they appear at different positions on the x-axis. And we say that they're less or more shielded. So I'll tell you what shielding means. So here's the x-axis of the NMR spectrum. Over this end of the spectrum with a low number of chemical shift, this is called the shielded region. So consider the molecule ethane. So these hydrogens here are close by to an electron donating methyl group. So that methyl group is donating a little bit of electron density, putting a little bit of extra electron density around the hydrogen, and that shields this hydrogen nucleus from the applied magnetic field. So it doesn't feel the applied magnetic field quite so strongly, and it appears down this end of the spectrum. If you compare that with chloromethane, now we've got a chlorine which is electron withdrawing, that is sucking electron density this way. So now these hydrogens over here are a little bit de-shielded, so they feel the applied magnetic field a little bit more strongly, and so now they appear more like here on the x-axis. And in a more extreme case, in fluoromethane, the fluorine is strongly electron withdrawing, so it's pulling a lot of electron density this way. So these hydrogens have very little electron density around them, so they're strongly de-shielded, and they really feel the effects of the applied magnetic field, and so they appear somewhere. So these hydrogens will give a signal somewhere around here in the NMR spectrum. So that's the concept of shielding. So different functional groups cause different amounts of shielding, and so this would be a typical kind of table of literature values that you would get in the exam. You don't have to memorize this. So depending on the various different functional groups, the hydrogens in those functional groups are shielded or de-shielded to different extents, and so they appear at characteristic positions on the x-axis here. So that if you have a signal in the NMR spectrum that appears in this region here, then you can be fairly confident that that signal will belong to an aryl group. Okay, I'm going to finish off with one last example, which is a bit more complex. So now this molecule here is tert-butyl acetate. There's the structure of the molecule there. And once again, we've got a little signal there from TMS that we can ignore, and there's two signals here that correspond to the tert-butyl acetate molecule. So this molecule has two sets of equivalent protons. There is one set of equivalent protons. Those three hydrogens there are the same as one another, but they're unique within the rest of the molecule. And then these three hydrogens up here are exactly the same as those three, which are exactly the same as those three. So all of these 9 hydrogens, we would say, form another hydrogen environment. And so overall, this molecule has two sets of equivalent protons. And that's why there are two signals in the NMR spectrum. This is the signal corresponding to protons A, these ones over here. And these ones, you notice they appear a little bit to the left along the x-axis, and that's because these hydrogens are a little bit de-shielded because of the nearby C double bond O, which is electron withdrawing. Whereas these hydrogens over here are not de-shielded because they don't have an electronegative atom so close by. So that's why signal A appears to the left and signal B appears to the right. And there's one more thing that we need to talk about that I haven't seen before, which is the relative intensities of these two signals. So this curvy line here is the integral. So if you measure the height of the integral there and the height of the integral there, that is proportional to the area under the curve, and that is proportional to the number of hydrogens that make up that hydrogen environment. So if you measure that distance 23 millimeters, 67 millimeters, that's approximately a 1:3 ratio, and that's exactly what you expect because there are 3 hydrogens in environment A and 9 in environment B, so that's a ratio of 1:3. So that explains the integral ratio there. Okay, so just to sum up, I've told you a little bit about what chemical shift is. That's the position on the x-axis, which indicates the chemical environment that a hydrogen is in. And I've also talked about the integration, which is proportional to the number of hydrogen atoms in a particular environment. We'll get on to the last point in class later on.